creating cloned animals. We're creating chimeric animals. We're creating transgenic animals. We're turning animals into chemical factories to produce pharmaceutical products. We're using animals as spare parts. These new technologies allow us to bypass all the boundaries in nature for the first time in history.
What has made all of this possible are breakthroughs in our ability to add, remove, or change genes in the spiral of DNA. The vast code that carries the information to create a living being. These advances in what is known as transgenics or GM technology have made it possible to create new animals. Similar techniques have already produced animals such as the geep, an animal halfway between a sheep and a goat. But scientists in the field have no doubt of the positive benefits of this technology and the potential impact on humankind.
The GM technology is very powerful. I think we'll learn to use it sensibly and usefully. It will revolutionize agriculture and aquaculture, in my belief.
But even now, the way animals are being changed is not always aimed at improving our health or well-being. Designer animals have already been created for our entertainment, changing the genes of mice so that the animals glow green under ultraviolet light. So where will this end up? How will the animals of the future be different? Our great-great-grandchildren celebrate Christmas in the year 2102 and wave a holographic hello to their parents on Christmas morning. As they excitedly open their presents, we can imagine that they have a surprise that currently seems impossible. But is it impossible? Our ability to change the size of animals could bring about a new range of exotic pets. Tiny elephants could be the fad of the future. Are we going to watch them as they play with children's toys? Incredible it may seem, but it is a future closer than we might suppose.
Oh, I think there's no question, but the transgenic technology allows you to alter the size of an animal so that the animal, when it's mature, will either be smaller or larger than it would normally be in the wild.
Norman MacLean wants to change the size and growth rate of the tilapia fish. It's an African fish which is caught in huge quantities in the developing world. In fact, it's the second most important food fish on the planet.
Tilapia is a strange fish in that, although it's a kind of luxury food in some countries like Israel or the state of Florida, in much of the world it is a poor man's fish. And so if you could make a difference, if you could make a significant change to the growth rate of tilapia, you would make a fairly major contribution to feeding the developing world.
And that's just what Norman has been trying to do.
It became obvious quite early on in the game of making transgenic fish that one would be able to enhance their growth rate by giving them extra growth hormone. So we set out to give fish extra copies of growth hormone genes.
Normally, growth hormone is produced gradually in small quantities. MacLean's idea was to introduce a gene that would increase the production and release of this hormone. Squeezing the abdomen, he collected the milt, the male fish's sperm, and used it to fertilize eggs taken from a female. An hour later came the critical step. Using a microscope to control a glass needle so fine it's thinner than a human hair, he injected the new growth hormone gene directly into the eggs. What was going to happen? The eggs turned to embryos, the embryos grew larger, the tiny fish started to take shape as their eyes and tails appeared, and then they grew further, and faster than the normal tilapia, and got even larger, until 3 months later, the result was dramatic. The transgenic tilapia on the right had grown to several times the size of the normal tilapia.
Really, the bottom line is not just that they're bigger, but that they grow faster. So it would mean that people could catch a fish which would give them a plate-sized meal probably in 3 months instead of waiting for 7 months.
In only 3 months, there is a huge difference in weight, with a larger genetically modified fish weighing in at 3 times the weight of the normal fish.
So, of course, you could produce very large tilapia if you wanted, and transgenic Atlantic salmon have been produced which are at least 10 times the size of normal Atlantic salmon when they are 2 or 3 years old. So I think there isn't a close limit to what size they could be.
Similar techniques are already being used to make mammals bigger. Merino sheep in Australia have been developed to grow half as big again and produce much more wool and more milk. But the introduction of a gene to increase growth hormone has not always had desirable results. In Beltsville, Maryland, USA, a modified growth hormone gene from a cow was introduced into a variety of pig. The pigs grew faster but couldn't walk, were uncoordinated, had arthritis, kidney disease, and pneumonia. Usually they died before the age of 8 months. Since this early experiment, the technique has been perfected, but the introduction of a single gene to increase the levels of growth hormone is not on its own going to be enough to create animals of a radically different size. To achieve this, many other genes will need to be altered.
It is necessary to discover all the genes which are responsible, which are involved in the growth process. And the better we understand the whole process, the better we can actually interfere with nature.
Although we think of it as a recent phenomenon, changing the genes determining size is not new. For thousands of years, humans have in practice interfered with the genetic makeup of animals, but by selective breeding rather than in the laboratory. By repeatedly choosing the smallest examples of a species and breeding them, genes are selected that code for a different size. Centuries of such breeding has made it possible to create fully grown horses, only 2 feet tall. And of course, it's not just horses. Traditional breeding methods are used in farming to generate very specific characteristics. A meat-producing chicken grows 6 times faster than the same type of chicken bred to produce eggs. Yet on its own, natural breeding is probably not going to be enough to produce radically different-sized animals. But if we could identify all of the genes involved, we could short-circuit the breeding process and engineer truly tiny or enormous animals very quickly. Lutz Bunger is on a hunt for those genes.
At the beginning, we were really interested in questions like how big can you breed a mouse? How small can you breed a mouse just by normal breeding?
So Lutz set out to create the biggest and smallest mice in the world.
A control mouse, before you actually start your breeding process, will be about of that size, which is a mouse which has roughly 30 grams.
Starting with his initial sample, Lutz bred larger and larger and smaller mice, so that he now has 2 radically different groups. The average large mouse is not just twice or 3 times the weight of the small mice, but 7 times the weight. And the largest mouse he has ever produced, at 100 grams, is 20 times the size of the smallest at 5 grams. Lutz's plan was then to look for which genes were different in the big and small mice. For they would be the genes which controlled the differences in size.
What we are using, of course, these high body weight mice and these low body weight mice to hunt for genes. So we try actually to trace down which genes are responsible for this line divergence.
Remarkably, Lutz has already been successful.
And we discovered already a few segments on the DNA which are obviously responsible for high growth and for low growth.
In principle, this means not only that it should be possible to intervene and change the size of mice, but that we could, in theory, alter the size of any animal.
You discover a gene in mice, you can use that information and you will find the same sequence in the other animals. And once you know that gene, you can actually use that information also for the other species.
With this information, could we, in theory, make a mouse the size of an elephant?
Elephant has probably 4 tons up to 10 tons. No one can actually predict how long it will take to get our mice that big. But it is, in theory, it is possible.
And if we can make a mouse the size of an elephant, is it only a matter of time before we make an elephant the size of a mouse?
I think it's broadly correct to say that the transgenic technology allows you to alter the size of an animal, either bigger or smaller, and it will depend very much on what the market demands and wants.
We have always changed the size of animals. And now we are using genetics to help us change the size of animals more quickly and more radically. We take tiny dogs such as the Chihuahua for granted. Will it be long before we are no more surprised by a miniature elephant? It is one thing to radically change the size of an animal, but the animals we create in the future may be even stranger. Rapid advances in genetics have meant that a race is on not only to change the appearance of animals, but to change their internal organs as well. Organs that could be used for human transplantation. Later this century, might animals be developed to produce all human body parts, from kidneys and hearts to even more complex organs.
I think it will be the biggest breakthrough in transplantation medicine. I mean, it has the ability to just transform the whole industry. From 2 perspectives. Not only will you not have to wait for people to die on the road in a traffic accident, that tragedy, in order to get an organ, now you'll be able to schedule your surgery. So people will be able to get access to organs because they're going to be unlimited.
There may be great potential, but are patients going to accept pig organs being transplanted into themselves?
I think the person on the street who's not sick at the time may have their own personal opinions about whether or not they would want a pig organ transplanted into them. But if you ask the people on the transplant waiting list, and we have, I mean, those people are like, sign me up. I mean, give me anything, because without it, they're going to die.
Right now, here in the United States, the go-ahead has been given to use pig hearts as xenotransplants for humans. And we've given the go-ahead on this. About 2 or 3 years ago, one of the leading xenotransplant people in the country came to me privately, one of the top universities, one of the pioneers. He said, "Jeremy, would you help us stop this?" And I said, "Why?" I said, "You're one of the pioneers." He said, "I now believe it's too dangerous."
Xenotransplantation certainly can be dangerous. Placing an animal organ in a human immediately raises the problem of rejection. In June 1992, a team of doctors in Pittsburgh undertook a unique piece of surgery. A 35-year-old man was suffering from a fatal liver condition. If he was to survive, he needed a new liver. Lacking any human donors, the team attempted to replace his liver with that taken from an animal. They chose a baboon, an animal close to humans, to limit the problems of rejection. The surgery appeared to be successful, But although in a matter of days the patient was awake and able to talk, it was not to be. 2 months later, he died from an infection. In search of a solution to the problem of rejection, researchers have turned to pigs. In March 2000, David Ayres successfully cloned the first pigs in the world, but he did so for a reason. He hoped they would help solve the difficulties of transplantation.
The main challenge now to using a pig organ in a human is that it would be rejected within 2 to 3 minutes. The blood system would stop, the blood would coagulate and congeal all around that organ, and it would just cease to function. And that's because of antibodies in the human that recognize that pig organ as foreign. And that's because of a sugar that's on the surface of all pig organs and cells that say, I'm a pig. And as soon as the human immune system, the antibodies see that particular sugar, they reject that organ.
It was already known that the sugar is placed on the pig cells by a gene in the pig known as the gall gene. David Ayres' idea was to get rid of or knock out this gene in pigs so pig organs would not be immediately rejected following transplantation. He first tried knocking it out of the strands of DNA contained in pig cells in his lab by making a small segment of DNA that finds the gall gene and replaces it with an inactive gene. After years of work, he was successful. The question was whether it would now be possible to grow a whole pig without this gene. And that's where his cloned pigs came in. David Ayres' plan was to take individual cells in which the gall gene had been knocked out and clone from them complete new living animals.
We need to know how to clone pigs because we need to knock out that gene in, say, a skin cell and use those to clone a pig.
The new pig might look like all other pigs, but lacking the gall gene, all of its internal organs would be different. They would no longer carry the sugar which identifies them as coming from a pig. As a result, David Ayres hoped that this would mean that if they were transplanted into humans, they would initially be accepted into the human body. Starting with the pig cells he had in his lab that no longer contained the gall gene, David set about cloning an entire pig by first creating embryos. Once the embryos had started to grow, a surrogate mother was needed for the pregnancy.
We do a surgical procedure to implant those eggs into the uterus of the foster mother. And she's been synchronized so that she's at the same stage as the egg, so that when they're given to the mother, they'll implant into her uterus and we'll be able to get a pregnancy established.
September 2001, and a number of pigs have become pregnant. But would the piglets be born with the gall gene knocked out?
I mean, we're very excited about these animals because they have the potential to be the first knockout animals born, the cells that were used to make them. So we're eagerly anticipating the birth of these animals in the hope that they will be able to overcome the rejection issues upon transplantation. Well, the unknown here is whether or not we have truly knocked out the gall gene.
All David Ayres now had to do was wait. 3 months, 3 weeks, and 3 days, the length of a pig's pregnancy, before he would know if the removal of the gall gene had been successful. But David Ayres is not working alone. 5,000 miles away in Scotland, Alan Coleman and his team who created the first cloned mammal of all, Dolly the sheep, is working on another side of the problem. For even if the gall knockout piglets are born, additional human genes will need to be added to the pig organs if the problems of rejection are to be overcome. And the team in Scotland has already succeeded in doing just that in sheep, but for a very different purpose. These sheep may look no different from normal sheep, but they carry a human gene. They are, to a very small degree, partly human.
There's always this issue, actually, when we add genes to animals. People say, well, how many human genes do you add to an animal before you impart some humanness to it? And it's a very difficult question. We don't know the answer, because we're not trying to make part human animals.
What Alan is trying to do is help patients like Martin Clark. Martin is just one of thousands of people who suffer from the genetic form of a lung disorder called emphysema.
I've had emphysema about 8 years now. It affects all parts of my life, my private life, my social life, my work life, because I'm constantly breathless. The slightest heavy task above normal walking on flat ground means I'm breathless and I have to stop, get my breath back, so it affects virtually everything I do.
Martin's condition is caused by an absence of a protein that the body makes naturally. The standard treatment for genetic emphysema is therefore to give this protein to patients. The problem is that we can't produce enough of this protein to supply all those with the condition. And that's where Alan's partly human sheep come in. Alan has succeeded in adding a human gene so that the sheep makes the human protein that Martin needs in its milk.
Congenital emphysema is caused by an absence of a particular human protein. We can make this protein in the milk of these transgenic sheep, and that's what we're doing in very large amounts at the moment with a view to satisfying an unmet market.
I have no problems with using animals to produce drugs. We use animals to eat. I'm a meat eater. I enjoy eating meat. I see no problems whatsoever with it. It's just another form, in the way I see it, is we take milk from cows, we take milk from sheep, but we use it differently when we inhale it. That's my thoughts on it.
From studios in Lynchburg,
Christmas Day 2001. Back in Virginia, there's some very special news. The first ever piglets are born with the gall gene knocked out. David Ayres had succeeded, but it's not the end of the story.
Well, just this simple step, it's not so simple, but actually just getting a gal knockout animal on the ground, that's not enough. That's only going to address the hyperacute or very early rejection stages. We feel we're actually going to have to add human genes, add a variety of different genes to the pigs, genetically modify them further so that their organs will survive for years when they're transplanted into a human.
When this has been achieved, the problem of rejection may be solved once and for all. But even then, Jeremy Rifkin is not convinced this will be the end of the problem.
What is the likelihood that viruses, in this case retroviruses, that are in the pigs transfer into the humans, recombine with human viral information, and create new viruses to which we have no immunity? We've already discovered 2 pig retroviruses. There are probably many more. So the likelihood that we're playing a dangerous game of health roulette when we cross that pig heart into the human is very real.
Alan Coleman is very much aware of the problem, but confident that it'll be overcome before transplantation takes place.
But we just don't know, and all these things have to be taken very seriously, thought through and researched before any trials of this nature take place.
Despite the problems to be overcome, both Alan and his colleague David Ayres are convinced the first transplants are going to be soon.
I think the first one will be the heart, possibly the kidney. There's some arguments that you may actually do it with the kidney first because it's not going to be a surgery that they're going to die from. In the case of a heart transplant, it's going to have to be someone who's really on death's door for the early clinical trials.
So we're probably just a few years away from modifying pigs to grow hearts and kidneys for human transplantation. In time to come, this may just be the beginning. There is little doubt that in the future, animals will be specially bred and farmed to provide a constant supply of spare parts for humans. Changing the size of an animal or its internal organs still means that the animal looks familiar in appearance. But maybe even that will change. In some future conflict in the year 2094, highly defended naval dockyard is under attack. In years to come, we might be able to modify animals to suit our purposes. Could we, for example, give a dolphin hands and thereby create an underwater weapon capable of a sophisticated attack beyond the capability of any diver or machine?
Few more years from now, then I think there is going to be a fair chance that we can manipulate animals in a way that as we would like them to be.
The first real evidence that it might be possible to change the limbs and appearance of animals came a decade ago. In Basel, Switzerland, Walter Goering was working with a humble fruit fly. Previous researchers had identified genes that created strange mutant flies that had double sets of wings and legs where they should have had antennae. But Goering went further. He altered a gene which controlled the position of the eyes and generated truly extraordinary deformities. Eyes on their legs and eyes growing on their antennae. From this work on fruit flies, it was possible to identify the genes that determined where limbs would grow. But on its own, this is not going to be enough if we are to grow hands on a dolphin. To do that, we'll need to change the appearance of the limb itself, and not just its position. And that's just what Stefan Mundlos is trying to do.
There's not a single gene that sort of makes my little finger, but there is a network of hundreds and thousands of genes that interact at different stages of development in different ways. And that's how we get this overall pattern, and that's how sort of the limb really forms and develops.
Stefan didn't set out to create mutant animals. Instead, he was hoping to solve the problem of human deformities, of which there are many types and conditions.
Generally, we are interested in the cause of human malformations. You can have, for instance, too many fingers, you can have missing fingers, the fingers can be too short, so these are the different kinds of malformations that you can have. And for many of these, there are genetic causes, and we want to find out what the genes are, and then try to explain how this limb deformity really develops.
In order to solve this problem, Stefan Mundlos turned to the mouse, whose genes are remarkably similar to humans. If he could work out how the genes in mice cause deformities, he hoped it might be possible to better understand similar genes in humans.
Okay, so this is a normal mouse. We can have a look at the limb and at the fingers of a normal mouse. And here she is, beautiful long toes, and this is what they normally look like.
Stefan had also found a mouse with a natural deformity.
This was an imitation that occurred naturally, just like it occurs in the human.
Having identified the gene he thought was responsible for the deformity in humans, Stefan set out to see what would happen if he knocked out the same gene in the mouse. How would the gene affect the mouse skeleton precisely? Which bones would be affected? And would it result in exactly the same deformities as in the human?
Here, a gene was removed. And that is also a gene which is important in the development of the fingers. And you can see that this mouse also has very short infused toes.
Stefan Mundlos may be on the way to understanding how we could control the growth and change the appearance of limbs on an animal. But could this really help us to grow hands on a dolphin?
Dolphins are certainly related to land animals. At some stage in evolution, what happened is that they went back so to say, into the water.
Millions of years ago, an ancestor of the modern-day hippo returned to the ocean.
Through many different steps of evolution, their hands and feet sort of regressed and became flippers.
All mammals share the same basic skeleton and therefore have the same framework of genes that could, in principle, be altered to create a hand.
You can change the shape. You don't change the overall principal pattern, but you can change the shape of certain bones. You make them grow longer, you make them grow shorter, and this is how these things work.
By making individual bones grow longer and shorter, it's possible to radically change the shape of an animal's limbs, as Lee Niswander has discovered by examining bats.
So there are certain genes that dictate how the limb grows and what type of pattern it gets. So the different genes that tell the limb to be the back of the hand versus the front of the hand, or how far to grow. And it's those questions that we're interested in getting at, looking at those same proteins, those same genes, but looking at how those are used in the bat.
Although we look very different from bats, and bats look very different from mice, we all share the same essential bone structure. Remarkably, it's only small differences in our genes, responsible for changing the way our bones develop, that makes us look different from either bats or mice.
So in us and mice, our hands look quite the same between humans and mice. But in a bat, these bones here are much longer than normal, as well as these other digits, so that essentially the hand is greatly expanded and much longer than we'd see.
The shape of the bones in human hands and mice feet have in the bat been changed so radically that they form the skeleton of the wings, with each of our 4 fingers being enormously elongated, while the thumb is reduced to a stub.
The genes that we're looking at are very fundamental genes. These are probably the same genes that are used to form a limb in all of us, essentially from humans to mice, to a chicken wing, to a whale flipper, to a fly wing. I mean, these are the same genes that are used over and over again in order to form an arm or a leg.
By manipulating a similar set of genes, Lee has been able to alter various animals, such as mice and chickens, so that webbing grows between their fingers or toes, making them just a little like a bat. If Lee could apply this same principle to bone development, it could have valuable repercussions for humans.
One of the applications that will come in the future is, let's say if by accident you lose a finger or you lose an arm. Because we know the genes that are important in making the limb grow and give it the appropriate pattern, maybe we'll be able to harness that information and then be able to take that back and be able to regrow a digit or a hand if it's lost.
And if we could manipulate the genes responsible for bone development, we could, in principle, turn a hand into a flipper or a flipper into a hand.
It's a very similar application. This information that we know could be used to change animals as we know them.
We are already able to change the shape of animal limbs. It may be only a matter of time before we know the detail of how to change a dolphin's flipper into a hand. In the future, we will change the size of animals. We will create animals with internal organs compatible with humans, and completely new animals with different form and appearance from any existing now. And we will be able to go further still. We will be able to change the way animals think and alter, therefore, what they're capable of doing. Could it be that in a time to come, animals will carry out tasks considered too risky or too dangerous for humans to undertake. Intelligence is not perhaps the first characteristic we associate with a mouse. But might it be possible to make mice better at thinking? Zhou Xian had an idea. When mice are young, they learn more quickly than when they get older. This is because the mouse, like other animals including humans, produces proteins in its first few weeks of life that encourage memory and learning, which it later ceases making. Zhou wondered what would happen if he changed the genes in mice so that these memory-enhancing proteins continue to be produced for longer. The first step was to inject the new gene into a number of fertilized eggs. The growing embryos were then placed in a mouse. 19 days later, some of the baby mice born were carrying the new gene. Was it possible that as the mice grew, the new gene would mean that their learning capacity would extend into adulthood and that their memory would be improved? Zhou set up an experiment.
This is a novel object recognition test. It's a way we measure the visual memory. And as you can see, this transgenic animal is exploring these two novel objects. They never see this before, and they tend to spend an equal amount of time exploring these two objects.
He did the same thing with a normal mouse. And then waited for 3 days. Would there be any difference in what the two mice would remember?
Now we try to see if the animal remember the objects he explored before. So the way we measure it is we replace one of the familiar objects with a novel one.
The normal mouse was placed in the box. It was equally interested in both objects, suggesting that it did not remember having seen the blue object before. In contrast, the mouse with a new memory gene concentrated on the new red object.
In the experiment, we find after 3 days, the normal animals were not able to remember the object he saw 3 days ago, where our transgenic animal is able to remember.
Remarkably, Zhou Xian has been able to increase the ability of the mouse to remember a past experience. And there's every reason to believe that if we're able to change the character of animals, we will do so. Already companies have started offering pet owners the opportunity to clone and potentially enhance their pets.
We've been simply deluged with interest from the general public in cloning their special animals, or at the very least, gene banking them.
This is champion Blazing Hamlet von Fitz. He's a smooth coat St. Bernard. He was born October 31st, 1993. And we think he's very friendly. He's a great companion dog. He does drool quite a bit, but that's okay.
Janice and Dale like their dogs so much, they're hoping to have him cloned. And if they could sort out a few defects on the way, so much the better.
St. Bernards are known to not have good hips because of the breeding over the years. And we've had him x-rayed by the Orthopedic Foundation for Animals. His hips are not bad, but they're not perfect. If they could do something to improve the hips on larger dogs, that would be just terrific.
We're underwriting research in corrective transgenics. And it's corrective in the sense that we replicate the animal, but we fix certain defects in the genetic donor. For instance, we have a list of the most common defects.
Hip dysplasia is a big problem. It's a result of inbreeding. It's ironic, in fact, that we're using advanced reproductive technology to fix a problem that results from human overbreeding, incorrect breeding in the first place.
Lou is not only planning to enhance the physical characteristics of pets.
Some traits are defined or determined by a very small number of genes, in some cases just a single pair. And in other cases, you might have dozens of genes or even hundreds of genes that go into determining a specific characteristic. For instance, intelligence. Intelligence is, although there may be single genes that have specific impact on it, especially specific types of intelligence, you may be able to amplify or retard memory or spatial visualization or whatever. But intelligence as a whole is a lot of genes.
But if we could change the intelligence of animals, would they really be able to carry out tasks that they're currently not able to do? Zhou Xian's latest experiment suggests the answer is yes.
This is what we call the hidden platform water maze task.
The tank is filled with opaque water. Beneath the surface is a hidden platform. Randomly swimming in the tank, it takes both the normal and the transgenic mouse almost 20 seconds for the mice to find the platform. Three days later, and the normal mouse still takes 20 seconds to find the platform. But the transgenic mouse remembers where the platform is and swims straight to it in just 9 seconds. Zhou Xian is confident this is only the beginning.
And in every single test we measured so far, they showed improved enhancement in those performances. So that leads us to conclude this gene indeed is a master switch for memory formation in the brain. And that also raises the possibility by enhancing and learning and memory function, someday perhaps there's a possibility able to improve the high cognitive functions, including intelligence, in the animals.
We are already changing the intelligence of mice, but would we ever attempt this with primates, our closest relatives? Well, we have already altered the genetic code of a primate. The first transgenic monkey, Andy, was born in 1998 with an extra gene. It was done simply to show that we could do it, for the gene has no intended effects. Might we go further?
Could we make chimps that are smarter so they could do service jobs? Well, the trick would be making them so smart that they could do service jobs, but not so smart that they demand their rights. So I don't think we want to get into that. But it's certainly possible to enhance intelligence theoretically. I don't think anybody has proven that it's possible now, and I don't think it would be moral to enhance the intelligence of an animal just to make it basically a slave class.
But might it not be only a matter of time? If we have the ability to change the intelligence of mice, isn't it only a little while before we're tempted to change the intelligence of our pets? And how long before we change the intelligence of other primates, so that they're able to carry out tasks we would rather not?
The mark of a civilization is how we deal with those who are powerless to speak on their own behalf. And in this entire debate on biotechnology, it's interesting to note how little attention, how little scrutiny we paid on our fellow creatures.
Anyone who's lived through science over the last 60 years is worried about the possibilities of science being misused. And yes, of course I'm worried about GM being misused. But if it's used sensibly and intelligently, then it will be of great benefit.
We're talking about 50, 60,000 pigs for saving human lives compared to millions of pigs that are slaughtered for people to eat. So I don't see the ethical debate there.
So you need to be very careful when you start tinkering with genes that you're not creating a suffering animal. That's the big risk, not that you're going to create some sort of Frankensteinian monster. We're pragmatists. We don't worry about playing God or other abstract concerns. We worry about creating suffering. That's our big concern, and because it's the biggest risk.
Whether we think it's a good thing or not, we are already changing every aspect of the shape and appearance of animals. We may not know for certain how the animals of the future are going to be different, but different they will be, and probably more radically and extensively different than we might currently think possible.
To celebrate the Bill's 18 years of groundbreaking television in Australia, the ABC is sending one lucky viewer and their guest to London to visit the set of the Bill and meet the cast in person.